Welcome to AP Podcast 7.5, the quantum mechanical model. Now, I got to warn you, it's going to get a little weird. But we're just going to try and touch upon where the idea of these orbitals come from. You guys know orbitals from last year, and you know they have funny shapes, but where did that come from? Well, you've got to remember, we've got de Broglie, we've got Einstein, we've got Bohr, we've got all those guys postulating ideas, trying to figure out the structure of the atomic structure of an atom and how it really works. We know that de Broglie said that matter could be like a wave. There are only certain allowed waves, and in the atom, those certain allowed waves were called electrons. Remember that Einstein talked about certain packets of energy, and Bohr talked about certain energy levels, so they're starting to get a feel for it. Now, Heisenberg comes in and says, you know what? There's a problem here. We can't really know where the electron is, or know its momentum at the same time. There's always going to be some level of uncertainty, thus his uncertainty principle. And so this led scientists to come up with the idea that, we're never really going to find out exactly where an atom is, but maybe we can come up with an idea on about where it is. So then Schroedinger comes in, and this is some hardcore math. We're talking about some serious calculus and physics and stuff that's way beyond me, but he uses a wave function to come up with these shapes that you guys know about, and those are just really probability areas. And so those probability areas we call orbitals, all right? Now they're 3D. Oops. They are 3D. They're not these little orbits like Bohr thought of. They are three-dimensional funky shapes. So they're very unique. So these wave function solutions give us the orbitals. And notice this part right here. Now it says solution here, but each orbital has a certain amount of energy. And those correspond to the energy levels we're going to be dealing with. So what does it really mean to us in AP? Well, it doesn't really mean a whole lot. We can't, they're not like hard walls where these orbitals are. It's something that just gives you a general idea of where an electron could be at any given time, kind of like a 90% kind of thing. But it does give us an idea, and that is a useful thing. So, but the math and physics and all that is way beyond us, so we really don't have to worry about it. What we do have to worry about, however, is that what's going on with the orbitals that have been developed. And this size that each orbital is just gives us a 90% idea of where the electron could be. Not for sure, but where it could be. And the first solution, and I got to apologize about this solution thing. I think I got this right out of the book. I'm not really too happy with that word solution. I'd rather have the word orbital. The first orbital is a sphere. And, of course, that's an s orbital, which you guys are familiar with. It looks like this, right? So you can imagine the smallest one is an s orbital in the first energy level, 1s. The second orbital, a second energy level, the third energy level, and so on. Now, after you get s orbitals, the next higher energy levels are the p orbitals. And for me, I like to think p and peanut. Peanuts have two little nodules, right? And these are on the planes of x, y, and z. And then we have the d orbitals. And those of you who have me before know that I think of this as a double peanut, d, except for this thing. Who knows what that's called? And then last but not least, f orbitals. And F for flower. Again, that's the Richardson word association. So just these, what's hard to believe is they've calculated these out in a three-dimensional space using some calculus and physics that's way beyond my brain to come up with these high areas of probability of where an electron would be. So, what's the point of all this? Well, we want to describe where these electrons are in the atom. The next step to that is to deal with quantum numbers. Now, quantum numbers are something that were developed, again, to give kind of like an exact location of the atom, or the electron in the atom. And so we've got 4 different quantum numbers. 2 of them give you most information, and the last 2 are something that's just kind of useful to know. But in AP, the first 2 are really important. The first one is the principal quantum number. And the principal quantum number is like the energy level, okay, or that main shell, whether it's a first energy level or the second energy level or the third energy level. So whenever you see n equals 2, we're talking about an electron in the second energy level. N equals 3 in the third energy level, and so on and so on. So that's the first quantum number. The next kind, now don't get all bent out of shape about this thing, angular momentum quantum number. Really, this is just the subshell. And when I'm talking about subshells, I'm talking about these guys right here, the S, P, D, and F. And again, those of you that did this with me last year, this is all review. If you've never seen this before, I'm probably not doing that great of a job of explaining it from scratch. But anyways, there's a number of ways to remember this, but honestly, I think you just need to get this memorized. Remember 0 for S, 1 for P, 2 for D, and 3 for F. These are the ones that pop up all the time in AP. If you want to know technically, the value has to go from 0 to n minus 1. What does that mean? Well, if I'm talking about something that's in the second energy level, n equals 2, right? That means we can only have orbitals of 0 and 1, right? Because n minus 1, 2 minus 1 is 1. So those are the 2 orbitals we can have. So we're talking about S and P orbitals. And if you really think about it, what kind of orbitals are in the second energy level? Only S and P. In addition, let's say n equaled 3. Okay, what L values could you have? You could have 0, 1, and 2. And this corresponds to S orbitals, P orbitals, and D orbitals. And if you think about electron configuration we've done in the past, what kind of energy levels, or pardon me, what kind of orbitals are in the third energy level? The 3s, the 3p, and the 3d. So those are the first 2 quantum numbers, and those are probably the ones that, at least in AP, you get asked about the most. I don't want to say they're the most important, because someone would probably get upset with me, but in AP, they're the ones that we get asked about the most. All right, and the next one is called the magnetic quantum number, and it has values of minus L to plus L, and it tells you the direction of each shape. So again, what am I talking about? Well, let's imagine I've got an energy level of 2, so n equals 2. So we know that L values could be 0 and 1, right? Okay, well, let's say we're talking about this one right here, and 1 corresponds to a p orbital, right? Okay, so that means for an L value, pardon me, an m sub L value, I could get minus L, which in this case is 1, 2 plus 1, and that's on the number line. So it looks something like this: minus 1, 0, and plus 1. Okay, now how many orbitals is that? That's 3 orbitals. How many p orbitals are there? There are 3 p orbitals. So it's almost like it gives an address for each individual orbital. I don't want to go so far as saying this is the x, this is the y, and this is the z, because honestly, I never had to do that in college. And again, if the professor's watching this, they probably want to butcher me, but really, this is about as deep as you need to get. Okay, and then the very last one is the m sub s, and that has to do with the spin. And I'm kind of getting ahead of myself because I'm assuming that you know about electron configuration, but if you guys remember orbitals, how many electrons can go in one single orbital? 2 electrons, right? One with a value of plus a half and one with a value of minus a half. So that's how we can describe all 4 numbers for every electron. And so we'll kind of do this a little bit, and you'll get the hang of it. So let's look at this question. What are the possible quantum numbers for the last electron of sulfur, electron of a sulfur atom? All right, well, sulfur has 32 electrons. So sulfur has 32 electrons, right? And again, I'm kind of, if you don't know about electron configuration, this isn't going to make a whole lot of sense to you. But sulfur has in the 3p, Okay, if we think about the three orbitals, I should do it like this, 3p. Sulfur has a total of 4 electrons in the 3p orbitals. Okay, so if we're talking about the last electron, we're talking about this one right here. Okay, so what kind of quantum number would I give it? Well, there's my energy. Oops, there's my energy level. So n equals 1. There's my orbital. That's L. L equals, what was the value for P? 1. Okay. And then the M sub L, again, you could argue that this is -1. Okay. Honestly, on AP questions, they usually don't ask you to. They usually accept any of the three values: -1, 0, and +1. And then the M, the M sub S would equal, since it's the second one, I'm just going to go -1/2. Honestly, in an AP test, they usually accept either +1/2 or -1/2. So that's kind of coming up with the quantum numbers for sulfur. Now, take a moment, you use your periodic table, write what you would write for the last electron of iron, and then we'll see how you did. Alright, so there's what I get for iron. There's 26 electrons, and the 3 is for the n value, d is for the L value, d orbital is equal 2. Then you've got a -2 because we're talking about this electron right here. Okay, this one right here. And then I gave it a -1/2. So something like that. Take a moment, try this one, see what you get. Did you do it? Well, there are the answers. Okay, look and see if those make sense. Please note that the bottom two right here, they don't work, right? Because look, you cannot, if you have a value of n, you cannot, a value of 3 for n, you cannot have that value for L. Doesn't work. Okay, so, and then this value right here, remember, if L is 1, you could have -L to +L, and so that doesn't work either. Okay, so hopefully you got those. We'll go over them in class, and it shouldn't be too bad. All right. Oh, yep. Let's just stop there. Do I want to stop right there?